Hey guys, welcome to R2E, and today in this video we are going to discuss thermal expansion, right? So all of you might be familiar with the thermal expansion, but those who don't know, let me first try to explain what is thermal expansion, right? So thermal means heat and expansion means to expand, right? To increase in size. So you might have seen that during summers, if you have a rod, then you might observe a slight increase in the size, but probably not enough to be observed through naked eyes. But you might see that the things are not fitting exactly into each other as they were used to happen in the winters, right? So thermal, the change in the values, like there is expansion in case of rod, there is expansion in case of a metal sheet, there is expansion in case of spheres, a metallic sphere, and not only in case of metals or not only in case of solids, fluids and gases also expand, but the expansion in case of fluids and in case of fluids is more observable than that of the solids, right? So now we are going to discuss the most simplest form of the thermal expansion, that is the linear expansion, right? The linear expansion. So down there you can see I have drawn two lines. Let's say the length of the line 1 and is L, and line 2 is L plus delta L. And what exactly happened between these two lines is that suppose uh, this line 1 it was a rod, and after that I heated it and the size increased to L plus delta L, right? And normally in the physics textbooks we are taught that this L plus delta L, which I should write as L prime. So L prime is normally given as L 1 plus alpha delta t, right? Where your L naught is the new length, your L prime is your new length, L is your initial length, and alpha is your coefficient of thermal expansion, right? By what factor your so your rod increase in length. To understand it simply, and delta T is the change in temperature, right? And now if I just open it up a bit, so I can write. So I'm going to just change the symbols a bit because it's getting uncomfortable for me. So I'm going to write L prime as L and L as L naught. So L equals to L naught 1 plus alpha delta T, right? And so I can write it as L equals to L naught plus L naught alpha delta T. So what you can see from here that if I plot a graph between L and delta T, wait for a second. Yes, if I plot a graph between L and your T temperature, then there is something very interesting going to happen. Here, if you observe this expression carefully, then this L is your variable, so I can write it as like Y. And here, your L naught is a constant, so I can write it as C. And again, your value of L naught alpha is again a constant, and delta T is again your next variable, right? So this could be written as X and this could be M, right? So this is a simple straight line equation, that is Y equals to mx plus C. So the supposed graph should be like this, right? And here the angle theta, and such that your tan theta, that is your slope, is equals to alpha L naught, and your this part is your L naught, right? But wait a second, because this is something we all know about it, but what's new about it, right? So let's discuss what's new about the thermal expansion. Now I really want to question that, is thermal expansion, as I told here, is really a linear function, that my length is a linear function of the temperature or something else? So let's try to explore it a bit more. So I have written that L equals to L naught 1 plus alpha delta T, right? So I will just do a bit of the maths and bit of rearrangement, and so L minus of L naught upon L naught is going to be alpha delta T. So so it's going to be delta L upon L naught equals to alpha delta T. Now for very small increase in temperature. So delta T will be nearly equal to zero. So like, or I could say delta T approaches to zero. Then I could write this whole expression as dl upon L naught equals to alpha dt, right? So let me integrate the both sides from L naught to L and here from T naught to T, right? It will turn out to be ln of L from L naught to L, again alpha T minus of T naught, and which will be, and here it will be ln of L upon L naught and alpha delta T. So I can write it just like that, L upon L naught equals to E alpha delta T, and L equals to L naught E alpha delta T. Now you can see that the expression, the relation turns out to be exponential one, right? So the supposed graph, so the graph is supposed to be something like, wait, this is L, this is your T. So your supposed graph is, so your graph is supposed to be something like this thing, right? I don't know if it's the correct graph, but it is supposed to be something like this. So what I have seen that, let me copy it.
All right, so now here we have two graphs of length as a function of temperature. One is exponential graph and other is a linear graph. So the question arises is that which one of them is correct? So technically speaking, this exponential curve is more correct than this linear curve. And but still we don't use this expression for evaluating our changes in length. We just use simply this expression to evaluate our to evaluate change in length. Now let us verify our formulas with some of the real life data. I want to calculate my L, and let's say my L naught is 5 meters. My alpha is 17 cross 10 raised to power minus 6 degree per degree centigrade, and I want the graph between delta T. So what I'm going to do is I'm going to plot a graph between L and delta T. First, using this expression, L equals to L naught 1 plus alpha delta T, and the second graph for L equals to L naught E alpha delta T. Well, let's plot the graph. So here is how I plotted my two graphs. So the red line shows the length expanding as a linear function, and the blue line shows the length expanding as a exponential function. So here you can only see the blue line, but just wait for a second and let me condense it. All right, wait. I'm not doing it in all proper fashion. So here we are now. So now I guess you can say your red line and your blue line. So you can see from here that the copper the don't show much of the difference. So until and unless you heat your metal up to 2000 degrees, there's not going to be much difference in the answers you get from the both of the formulas. So wait, so both of these are correct up to nearly 2000 Kelvin difference, right? So now you might ask this, but how is that even possible? Because the answer from this function should be very much less than this function. Well, this is one of the most fascinating parts of the mathematics, and the answer lies in the concept which we call as the Taylor's expansion. and probably it's going to be the topic of my next video. So till then, goodbye and stay tuned.